Hello. So at this point we've talked quite a bit about probability and we've worked a quick example in the context of a lecture. Let's do a little more just example work with using probability in the context of the normal distribution. So if again, imagine I have a measurement series. So let's say let's imagine Let's imagine you've got a series of measurement, some sort of a measurement tool. So let's say a set of calipers, for example. So calipers measure and let's assume that there's some standard deviation on that with, let's say, 0.0005 inches. All right. So now we could imagine that the measurement were 4.922 inches, right? So calipers typically give, in inch measurements, they typically give three significant figures after the decimal point. The better the calipers are, the narrower this will be. The cheaper the calipers are, the wider this will be. Cheap calipers will not give you anything this good. Cheap calipers, if you get a thousandths of precision, you're doing pretty well. Cheap calipers typically will be 1 or 2, even though they report 3 decimal places. That doesn't mean you can trust them to 3 decimal places. Let's see. So far we've learned how to calculate the probability of something, but this problem asks us to go backwards. So far we've learned how to say, all right, what is the probability that x is equal to x1 to x2? We've learned how to do that, and so we want it to be 0.95. So the question is, what are x1 and x2? In this example problem, we have to go backwards. This is a pretty realistic problem. Basically, you've got a measurement device, it's given you an answer, and you want to say, all right, but what is the window in which I am 95% confident the real value lies, right? So this is the way we will approximate it. We will give it the benefit of doubt and say, what if the expected value were exactly what I measured? And we will say, what is the probability that the actual value lies here? Now, everything I'm saying is an approximation. The real theory of what we're talking about is more complicated, but this is actually a pretty good first order approximation. So here we go. So if so this is the case, what we would want to know then is how do we choose x1 and x2? So in our scenario, we'll turn this into z in a minute. Let me put it in terms of x first. So we've got to break the x-axis, because when we get way out here to 4.922, it's basically 0, and then wow, around a half a thousandths wide. There. So that's our probability distribution function. And it can be really tight because maybe we've got a nice set of calipers. That's great. But it's not infinitely tight. There is some uncertainty. And there are situations where 0.5 thousandths of an inch is an unacceptable amount of variation. This would be an inappropriate tool for that job, right? So you can't just assume this is infinitely accurate, right? It depends on your application as to whether or not this is applicable. I didn't ask that. I didn't ask what's the application. I said, establish a confidence interval. That is a range in which I believe X will have its, in which I am 95% confident that the real value lies. So what we will do then is establish a range plus or minus some delta X. And there, the area under that curve needs to be 0.95. That's the problem we need to solve. Well, so X bar plus or minus delta X, or here's the easier way to do it. Remember Z? We said Z was equal to well, if I just solve for X in terms of Z, right? If I go backwards, then X is just equal to X bar plus sigma times Z, right? So how far am I away from X bar, right? So what we want to do is figure out over what range of Z would this area here be 0.95, right? So plus or minus there we go, plus or minus Z equals 0.95. Well, this is totally doable. I just need to use my integral tables. Click, there they are. Nifty. So we're on the integral. So now I need to go backwards. I do not look up 0.95 for Z. No. That's the value that the integral of this curve needs to be. So in other words, I need 0.95 to be in the body of the table. Wait a minute. The largest number here is 0.499. Oh dear. What did I do wrong? I have goofed up, haven't I? Well, no, I haven't. Remember that this integral here is only half of the picture, right? So we need twice this value to be 0.95. Ah, okay. Well, that's doable. So in other words, I need this part over here to be half of 0.95 or 0.475, right? Yeah, totally. So half of this, how to shade this in. So this half here needs to be 0.475. That I can do. Click. All right, so 0.475. If I look around in this table, let's see, here's 0.473. Oh, there it is, right there, 0.475. All right, let's see, so that's 1.96. So the probability that Z so I know this is true. Now you don't have to write this out. I'm doing this so and then the probability that Z will be equal to plus or minus Z1 is twice this, or 0.95. So in other words, my measurement then, I would say, is equal to my expected value, which was 4.922 inches, plus or minus sigma x times z, which was, I'll substitute in for these in just a minute, or 0.922 plus or minus 0.0005. There we go. Let's get that over here where you can see it. Times 1.96. Okay. Let's go back to the camera. Excellent. Not so bad. Running out of space. All right, just quickly, I pull up my handy dandy calculator. By that I mean Python. This is actually not too bad, really, but well, why don't I just use the calculator, make sure I don't make an embarrassing lapse of mental math. Let's see, 0.00098. I would call that a thousandth. There we go. Now this is called a 90, so this is a 95% CI, confidence interval. This here is a 95% confidence interval. So in other words, I took a measurement and I am 95% confident that the measurement is within this range. So if you ask me, is the part smaller, that is, if this were the diameter of a shaft, and you asked me, can this part fit in a 0.9224 hole or 923 hole, right? This allows you to say, yeah, I'm 95% confident that'll happen. Well, that still means you'll be wrong 5 out of 100 times. So you might actually want to shoot for something higher than that, right? So this is, and the way that impacts your reporting is right here. But this answers the question that we posed. The question was, what is the 95% confidence interval for this measurement? And we just answered that. All right, thanks for watching.